Welcome back, students. From today we are going to enter inside our mainstream subject of transducers engineering. Till now we saw the different common qualities of different systems that are first order system, second order system, zero order system and all these things. And the systems also represents the sensors. But from today the second unit starts and these deals with the resistive transducers. You have been already introduced to what is a transducer and how energy is transformed into electrical energy. And different types of transducers all have been introduced to you in the unit number 1, and from today we are going to start up with the resistive transducers. Resistive transducers. So the transducers are divided into several things, as you have seen. Depending upon their working, they are divided into resistive, inductive and capacitive, Hall effect, magnetostrictive, fiber optic, like this. There are different, but the major three categories of sensors that works in the world are 90%, okay, fall under the categories of resistive, inductive and capacitive. So only you have been given the major allocation of big cake over for the resistive, capacitive and inductive in your syllabus. And this 3 covers the 3 units, and to start up with, we start with the resistive transducers. Okay, already you have been introduced to the word resistance. The resistance is the property of a material to object the flow of current. Okay, so that is the resistance. So with this principle, these transducers are going to work. Okay, so hence these are called as resistive transducers. So there will be, for an input change, there is going to be a, imagine this is your system or a sensor. Here afterwards I won't use the word system. Here is our sensor, where there is going to be a physical change and then that is going to be a resistive change, resistance change. This is called as the resistive transducer. When there is going to be a physical change or a physics parameter, there is going to physical parameter in the external world is going to change, then there is going to be a resistance change that is going to occur there in your system. So hence these kind of transducers are called as resistance transducers. In this, there are several categories of resistance transducers itself we are going to see. One is the potential transducers, that is the potentiometers. Then you have your strain gauges, load cells, okay, are all some many different kinds of transducers that you will be covering in our syllabus, and how these can be transformed into voltage also will be taught to you. To start up, we are going to measure displacement. Okay, because I start up instead of taking directly the sensor and showing you the change of resistance, let us take the parameter that we are going to measure. This is displacement. The displacement is divided into linear displacement and angular displacement. Okay, the linear displacement, what is displacement first? You have to understand, before getting inside what is displacement, you need to know what is the difference between distance and displacement. Okay, take 2 points A, B. Okay, the minimal length between these 2 points covered is called as displacement. You can travel from A to B in the, this is the minimal way that you can travel, but you can travel in many different ways like this. If the distance between A and B is 5 kilometer, but this route will take 20 kilometers. The distance can be told as 20 kilometer, but the displacement that has occurred is only 5 kilometer. Okay, because here it is happening in one direction. Here direction is included inside your quantity. Hence, the distance is a scalar quantity and the displacement is a vector quantity. Okay, so we are going to measure this displacement now. Okay, we will be able to detect both the what is the vector quality and the scalar quantity. The scalar quantity will gives you only the magnitude, and the vector quantity will have both magnitude and direction. Okay, so here using our transducers or the resistance type of physics transducers, we will be able to measure both the magnitude and direction, that is the result of the displacement that is going to happen. Okay, hence it is the linear displacement. First we can see. Let me start up with linear displacement. Okay, for the measurement of linear displacement and angular displacement in resistive transducers, there are several different kinds of transducers in inductive type, capacitive type, and all these things. Now we are going to concentrate only the resistance changing transducers. Those are the resistive transducers. So the main first basic transducer that we are going to see is our potentiometer. Okay, the potentiometer is divided into three types. One is the translational potentiometer or pot. Your pot, then rotational type, then helical type. These two are rotational or angular displacement measuring devices. Angular displacement measuring. This is linear displacement measuring. Okay, so we have our basic transducer, that is the potentiometer, which is divided into three categories. One is translational, rotational, and helical. And the translational is used for the linear displacement measuring. The rotational and helical are used for the angular displacement measuring. Okay, linear displacement is shown with meters or centimeter, like that. Angular displacement is in degrees, radians. So you understand now we are going to measure the displacement, that is the linear displacement and angular displacement, using the potentiometer. First I will show you an experimental demonstration how resistance varies with respect to a change of a physical quantity displacement, that is a linear displacement, and we are going to get introduced to a linear changing potentiometer. You might have seen this device. Okay, you might have seen this device in your elementary school, which is called as a rheostat. Okay, this rheostat is used there in your schools. You might have used it for changing the, or as a voltage dividing circuit, in that it will be used, but here we simply use it for measuring linear displacement. Okay, you see here, now you have a potentiometer. This is a linear potentiometer or a translational potentiometer. You have your three knobs. I'll show you. You have, here is one knob, here is one knob, and here is one knob. Okay, these three knobs are there. These two knobs, when you connect and check, you will get the full resistance what is covered by this entire rheostat. and this is your sliding knob where we are going to give the displacement, okay, and you will be able to check the change in resistance. Okay, now this is a simple multimeter where we are going to check the resistance. See the resistance that is shown over here. Actually, this is the end point. More than this, I can't move this slider. The slider, with this slider, we can change the resistance of this setup. These are coils are wound over this. You can very well see here, coils are wound, and this is the minimal side. So I have connected it over here, and when you increase the distance between this side to this side, the resistance increases. Okay, so here actually you should get 0, and here you should get the maximum. Here please point out here, I am lifting it even to a higher level. It is 350, it is written over there. Okay, here it is written 350 is the maximum resistance of this rheostat. 350 is the maximum resistance of this rheostat. So 0 is over here and 350 is over here. We can just check. But this is a very old rheostat, so we get an error at the end. 4.3 is an error that is occurring. Instead of 0, we are getting 4.3 over here, and I start moving. And before that, I have to tell an important thing. Now, what is the distance between here and here? It's exactly equivalent to 1 feet, 30 centimeters. Okay, you see here, are you able to notice that it's 4.1? I start moving. Slowly the resistance is increasing. At the maximum, it will have around 360. Okay, there is again a 5.1 as an increment error. Okay, if I again come back, it's going to decrease and it will come to 4.1. Okay, come to 1.7. Okay, so now you can very well see this is the linear. Now you are able to match your displacement that you are making. This is the displacement. Let us take the distance from here to here. What you have made is 5 centimeter, and you are getting an increment of 44.2 ohms for this 5 centimeter increment in the displacement. Why you are saying is that displacement, you are moving it in one direction only. If you go back, you will be able to see this reduction in resistance, and you are able to identify the displacement has occurred in the back direction. Okay, that's a cancellation or negative displacement is happening, and you are seeing a reduction in resistance. So with this increase or decrease in the reduction in resistance, you will be able to identify the displacement that is happening over there in linear motion. Okay, so either you can increase it in this direction, it will be increasing, or it will be decreasing. Okay, now you can imagine where it is applied in a practical fashion. You can imagine a machine which is moving the slider, okay, like this. There is a machine which is moving the slider, and you want to see a robotic arm which is moving the slider, how much it has moved, okay, the slider. All these things can be measured using the resistance. You can take this resistance and connect it to a Wheatstone's bridge, which will convert this. We will see how a Wheatstone's bridge converts the resistance to voltage. You might have already studied also in your 12th standard, and also you will be introduced to a Wheatstone's bridge in your measurements and instrumentation syllabus. There you will be converting any kind of resistance can be converted to an electrical voltage using Wheatstone's bridge. Inductance can be connected to a Maxwell's bridge for converting it into electrical signal, and a capacitance can be converted into electrical signal using your Shering's bridge. Okay, so here you can convert your resistance change to a electrical voltage using the Wheatstone's bridge. But here that is not the main thing. Here the displacement, what is happening either in the positive direction or in the negative direction, has been transformed into resistance. Okay, positive direction is increasing, okay, and the negative direction it is decreasing. That's translational motion. Okay, so here we have seen about the increase or decrement in the translational or linear displacement. Okay, when we want to see it in rotational displacement or angular displacement, I will show you the other types of potentiometers. This is a translational potentiometer or the rheostat. We will go for a rotational potentiometers. We are having different kinds of potentiometer. Here 4 different kinds. Okay, first let me start with the basic type which you will find everywhere. The rotational potentiometers are divided into 3 types. Sorry, 2 types. The rotational potentiometers are divided into 2 types. One is the normal rotational and another one is helical potentiometers. Okay, so this is a normal rotational single turn potentiometer which is comprising of 1 ohm. 1 kilo ohm is the maximum. So 1 kilo ohm is the maximum, and you can see here I am making a turn. I am making a turn and there is an angular displacement that is happening either in the one side or in the other side, okay, which makes a change. When I make a change in this side, it is increasing, and in the other side it is decreasing. Hence we will be able to say in which side we are making a change, whether it is a positive side or the negative side, whether in the incremental side or the decremental side, by seeing the change in resistance, we will be able to say whether it is in the one direction, the positive direction, or in the negative direction. Okay, so this is we are able to see the displacement in degrees, that is the angular displacement. This is a simple mica based angular pot, that is a rotational potentiometer. I just turn the knob. You please notice the multimeter reading, it is increasing and it's going till 1 kilo ohm. So when it is 1 kilo ohm, it is 360 degrees. When it is totally 0, it is around 0, ideally 0 degrees, but there will be an error again. There will be an error gap, something like a sector. It will be like this. You can go till here it is 0 degree, 0 ohm, and here it is your 1 kilo ohm, and here you cannot change your knob. Okay, this is what is happening here. This is this much I can change, and there also there is an error of 8.4, but when I increase it, this is this much. Notice here, and I can go till here, and there's a sector which I cannot move, and it is 1 kilo ohm. Okay, so it's a single turn angular potentiometer. Next comes our multi-turn or helical potentiometers, which are for very precise measurements we use this, and this is also higher I have for 1 kilo ohm. See here, it's at its minimal end. I am going to change, it is a 10 turn potentiometer. Here you had only one turn for your 360 degrees, only you had for your 1 kilo ohm. Okay, here the same 1 kilo ohm can be expressed as in 10 turns. So each turn corresponds to 100 ohms. See here, this you see it's 100 ohms. Like this, I can make 10 turns to bring this to 1 kilo ohm. I made 10 turns to make this to come for the 1 kilo ohm. Again I am coming back. Okay, for very precise measurements we can use this for fine tuning and also finding the displacement, that is angular displacement, that is happening in a very precise manner. We can use this kind of potentiometers. This is a helical potentiometer, as I explained you. Helical potentiometer, this is helical potentiometer, this is a normal rotational potentiometer. Inside it has many windings. Okay, here you saw many windings in a translational part. Like that, inside it will have many windings, so that you get this kind of a effect. These other parts are for PCB applications. These are simple small parts. See here, it is, you can change this. Again, this is also a 1K part. I am reducing it, it's coming down. It is a single turn again part. I'm just changing the screws and it's coming to 1, 2. You see, it's a minimum, that is 3.0 it is showing, and if I go to the maximum it can go till 1K pot. Like this, this is of another style. Trim pots, these are called. These are very useful in PCBs, printer circuit boards, you will study. This is a 10 kilo ohm pot, so only you can again make many adjustments possible. See here, I can go till many turns and it goes till 10K. It's also a helical pot. Inside it has many turns inside we can make, and we can make many precise measurements. So from this itself you can see I am making many turns coming down now. Beautifully, for each turn it gives 1 kilo ohm reduction, and 10 turns can be made for from 1 to, I am making it fast, it will go to 0. So it's an extremely precise pot. Okay, it's at its minimum condition, so it is 0.6. If you want to increase it, we can again put it to screw and we can increase it. These are very cheap, these are very costly, these are very cheap, but they are very not precise. These are very precise and they are little costly. These are cheap and also precise. Okay, so only we use it in PCB boards. So now you have been introduced to many different kinds of potentiometers. Our translational potentiometer, the rotational potentiometer, helical potentiometer, then these are also the rotational single tone rotational, the multi-turn helical potentiometers, where we are converting the displacements, the linear displacement to resistance. All these are for the rotational or angular displacement to resistance. Okay, so with this I conclude the lesson number 1, and from tomorrow we will see the other kinds of measurements in resistance, like measurement of force or pressure and all these things, how we can measure using the resistance transducers. Thank you.